Hi, I'm Andrew Wells, a doctoral student at Rice University. I'm going to talk to you today about LTLf synthesis on probabilistic systems. This is joint work with Morteza Lahijanian at CU Boulder and Lydia Kavraki and Moshe Vardi, both at Rice University. So what is synthesis? Informally, the synthesis problem is, given a high-level specification, build a construct by construction low-level implementation. Previous work has considered both reactive and probabilistic synthesis. We present the first work on probabilistic LTLf synthesis on MDPs. I'd like to note that code and examples from our paper are available on GitHub at the following address. Many systems in the real world are stochastic, meaning they have uncertainty that is modeled as a probability distribution, and we build a markup decision process, or MDP, to reason about these systems. The goal for probabilistic LTL synthesis is to find a policy over this MDP-M that maximizes the probability of satisfaction of some LTL formula. And we solve this problem by composing the MDP with some omega automata. The first question I'd like to address is, why are we interested in LTLf? So the problem of MDP synthesis with LTL has been well studied. There are mature tools such as Prism, which we'll use in this paper, which have 213 citations as of today. So I guess our paper is the 214th citation of Prism. And these tools have successfully used LTL or PCTL with MDPs. However, LTL and PCTL are both defined over infinite traces, which works well for something like networking, where you want a computer network to run infinitely over time, and you want to ensure some property like having no deadlocks occurs with that networking protocol. But in other domains, such as robotics, we're typically interested in finite traces, things that have to happen in a finite amount of time. And this is why we use the logic LTLf. So that's why we're interested in LTLf, or finite synthesis. And I'll move on to define the syntax of LTLf. So the syntax of LTLf is the same as the syntax of LTL, if you're familiar with that. But basically, we have a set of atomic propositions prop, and we allow the Boolean operators, negation, and conjunction, and then we have two temporal operators, next and until. And the semantics of LTLf differ from the semantics of LTL. And the important thing to note here is the trace row has a length, so we have the length of row. And we're also able to talk about the ith position in a trace row, and we say that row comma I is a model of psi if the ith step of row is a model of psi. So we have these first four rules, which are standard to LTL and make sense for propositional logic. So basically, if at any time step we say that proposition P is true, then P has to be true at that time step, and so on and so forth. The two interesting cases compared to LTL are the last two. So on the next operator, we insist that the length of row has to be greater than I plus 1, and then we say that next psi is true if row at time step I plus 1 model psi. And for the until operator, we insist that there has to be a j before the length of row, so j greater than or equal to I and strictly less than the length of row, such that at time j on trace row, psi2 is satisfied, and then the normal until condition that for all k greater than or equal to I and strictly less than j, row k is a model of psi1. So in previous work, we considered reactive synthesis on LTLf, and we showed that using a symbolic approach with specific tools built for LTLf is generally faster than tools built for LTL in a reduction to LTL. And we're able to solve reactive LTLf synthesis via a reachability game on finite automata. So a markup decision process, or MDP, is a tuple of S, which is a finite set of states, A, a finite set of actions. We say that A of S denotes the set of actions that are enabled at some state S. P is a transition probability function, so given a state and an action, we transition to another state with some probability between 0 and 1, and we constrain it so that it's a valid probability distribution, so it has to sum up for 1 for all of the state actions that we consider. S init is an initial state, AP is a set of atomic propositions, and L is a labeling function for each state, telling us which atomic propositions are true at that state. So we'll consider an example MDP. Here we have 4 states, S0 through S3. On these states, we have some actions, A0 or A1. And here all of the actions except A1 at state S0 have probability 1 of transitioning to another state. For S0, action A1 has probability 0.5 of going to S1 and 0.5 of going to S2. And then above each state, we've written a set of the propositions that are true at that state. So in S1, the proposition P1 is true, and proposition P2 is false. At S2, both P1 and P2 are true, and at S3, neither P1 or P2 is true. Now an important point for our work is how we're going to define satisfaction on this MDP. So this MDP may have infinite runs, but we have a specification which is over finite traces. So we have to define what it means for an infinite run to satisfy a finite trace. And we do this using prefix satisfaction. So we say that a run satisfies a formula if there is a prefix of the word induced by the run, such that the labeling of that prefix is in the language of our formula. This allows us to define the LTLf synthesis problem on MDPs. So given an MDP-M and an LTLf formula psi, we want to compute an optimal policy pi star that maximizes the probability of satisfaction of the LTLf formula psi. And we're also interested in computing this probability, so the probability under our optimal policy that we satisfy psi. We present 2 pipelines for solving this approach. So the first is via a reduction to existing LTL tools, and the second is by applying specialized LTLf tools to the problem. And our goal with this paper is to evaluate whether it's worthwhile to develop these specialized tools, or whether the mature tools for LTL that already exist are sufficient for solving the problem. So the key idea behind the LTL approach is an augmentation of the MDP, and this is easiest to explain with an example. So here we have the same MDP as before, except that we add this new state, S term, and we add new actions A term from every state in the original MDP to S term with probability 1, and also as a self loop on S term with probability 1. So I'm omitting the probabilities on the dashed lines going to S term, but all of those probabilities are 1. And then we also add a new propositional variable, alive, and we set alive to true in all of the states of the original MDP, and we set it to false in state S term. So S term will just be an empty set for the labeling function, and otherwise the MDP remains unchanged. The second part we need for using existing LTL tools to solve the problem is a translation from LTLf to LTL. So we're going to translate an LTLf formula on M to an LTL formula on our augmented MDP M prime, and we do that sort of in 2 parts. So we have this function t that I'll talk about in a bit, and then we have this second clause. So it's a conjunction of this function t on the LTLf formula and the clause that alive has to be true until globally not alive. So alive remains true until it becomes false, and then it stays false forever. And the first part of that clause is this function t of the LTLf formula. So here basically we're saying that for propositions, they have to be true while the trace is alive. Negation also will inductively be true while it's alive, same with conjunction. And then for the temporal operators, if I say next psi, that means that there has to be another step in my trace. So alive has to be true at the next step, and then the translation of psi. And the same thing with until. So if I say psi1 until psi2, it means there has to be another step in the trace where psi2 is true, and the translation of psi1 has to be true until that point. One thing to note here is that some things that would be tautologies in LTL are no longer tautologies in LTLf. For example, globally next true is a tautology. So now we introduce the theoretical results from our paper. These aren't especially deep or surprising. Most of our contribution is in the empirical side. But basically what we aim to show here is that the augmented MDP in translation to LTL will correspond to the problem we solve with specialized native tools. So we're going to have this lemma talking about finite paths and a correspondence between the MDP-M and the augmented MDP-M prime with finite paths. And this basically claims that we can go back and forth between the two by considering the alive variable and policies that set alive to true as soon as we have a satisfying prefix in M prime. And one thing to note here is that this is only true for maximization, not minimization. And the reason for that is that when we're trying to maximize a policy, taking the action A term to go visit the state S term, A term always has probability 1. So you can never reach a greater probability by avoiding the state S term until a later moment. Then to complete the theory of our paper, we have a theorem, which is just an application of this lemma over the set of finite paths that satisfy some formula. So given some paths that satisfy the formula, we're able to look at a finite set of paths and then apply the previous lemma. So this shows that we have a correspondence that correctly reduces from LTLf to LTL, and we can go between those two. They'll give the same answer. And one thing to note here is, again, we don't have minimization, and that means that while we present something that sort of works for maximizing synthesis, we're no longer able to do verification as the dual problem of synthesis. We're not able to find the minimizing policy for the same LTL formula. So now that we have our two approaches, we want to consider some experiments and see how well they work compared to each other. In choosing our experiments, we found that it was difficult to get a representative sample of finite trace benchmarks. Most benchmarks on synthesis on MDPs are over infinite traces and sort of don't make sense in finite trace settings. So for example, Dining Philosophers, which we'll talk about later, doesn't make sense in that you're trying to find versions that avoid deadlock, and in finite traces, deadlock doesn't really mean anything. We also found that randomized formulae don't work well on MDPs, so if we just choose some cells in a grid world and then randomly try to visit some and avoid others, we more than 98% of the time end up with tautologies or contradictions, so either 0 or 1 for the probability of satisfaction. So those aren't especially interesting. So we're trying to choose benchmarks that sort of capture the properties that would naturally be expressed in LTLf on problems that would sort of naturally be of interest to us. And we're going to consider the complexity of both the MDP, because we have to make some changes to the MDP, and of the formula. So one set of benchmarks is a classic Gridworld domain. So here we have some grid where a robot can move around, and the robot can move north, south, east, or west, and every time it tries to move, it has a 69% chance of moving in the desired direction, a 10% chance of moving either left or right relative to that desired direction, 10% chance of staying in the same cell, and a 1% chance of going backwards from its desired direction. And based on that, we can build a grid world with some hallways in it the robot needs to navigate, and a grid world with some random obstacles it needs to navigate around. And here we have sort of a typical robotics LTLf task. So we give it some set of locations we want it to eventually reach, and then we also have some regions that are bad, and we want to globally avoid the bad regions. Here the graphs are showing the runtime of each of the approaches. So we have the native or the default LTL pipeline with Prism. We can also import automata through existing tools. So we've tried Spot and several other tools and found that both Prism's default and Spot are the best. So those are the two we show. We can compare that to our native method. And here the runtime of each of the steps of Prism is shown notice that the automata loading is only reading the automata from hard disk in the native approach, so that's not shown in either the LTL Prism or LTL Spot approaches. So one thing we want to consider is different sizes of grid worlds. So here we have the same formula I showed on the previous slide, and we consider a 10 by 10, a 50 by 50, and a 100 by 100 grid. And here we see that while there is some advantage to using the native approach, the model construction time for these MDPs sort of dominates the runtime, so the advantage becomes relatively small. If we fix to the 10 by 10 grid world and consider changing the length of the formula, so the number of regions we want to visit, we see that we have sort of a break-even point at 3 regions, and then we have, for larger and larger formulas, the gap widens, and eventually once we get to 10 regions, Prism's built-in method runs out of memory, while the native approach is able to solve the problem relatively quickly. And the native approach doesn't run out of memory until we get to 18 regions. Next, we consider some benchmarks that are not grid worlds. So here we're considering the famous randomized dining philosophers benchmarks from the Prism tutorials, but in the specifications for the original benchmarks, we're interested in a lack of deadlocks over infinite traces. So here we sort of had to come up with a contrived example of just making sure the philosophers each eat once on the left, and then eating at least once with some order on the right. And this, in my opinion, is the most interesting experimental result. So here we found on the left that Prism outperforms both Spot and our native approach significantly. And when we sort of dug down into this with the help of one of the Prism developers, we saw that the automata sizes for both Spot and the native approach are, for Spot, slightly smaller, and for the native approach, significantly smaller than the automata used in Prism. But the internal runtime in Prism is still faster with a larger automata. And this suggests that we might need to consider not just using sort of black box automata generation tools that will give you the smallest automata, which is sort of the naive idea of this is the best automata for algorithms using an automata. But maybe we have to consider integrating it within Prism such that we find automata that will work well for probabilistic synthesis. Finally, we consider 2 randomized games. So first is the game of NIM, and we consider it with a height of 200 and see that the native approach is much faster than both Prism or Spot. And we consider a 4-bit counter game where there are 2 4-bit counters and you try to get the counters to match up. And we again see that Spot times out after several hours. Prism runs out of memory, but our native approach is able to solve the problem very quickly. So for future work, we'd like to resolve this lack of minimization. So we'd like to modify the LTL approach in some way that would allow us to perform minimization/verification. We'd also like to examine a closer integration of an LTLf tool within Prism to alleviate the problem we discussed with the dining philosophers, where some automata that's smaller is still giving worse runtime results in Prism. And one possible approach to try to more tightly integrate LTLf tools within Prism is using symbolic products of our symbolic automata, which we generate with the tool, and the symbolic MDP, which Prism generates. And we'd like to expand LTLf on stochastic games. So in conclusion, I presented the framework for LTLf synthesis on MDPs. We compared existing mature LTL tools to specialized LTLf tools and showed that frequently these LTLf tools are faster, and we've made our code available on GitHub, so if you have properties that can naturally be expressed over finite traces, we'd urge you to try using these LTLf tools and hopefully find a runtime improvement for your problem. Thank you.